Good morning, everyone. I'm Cédric David. I'm a research scientist at NASA's Jet Propulsion Laboratory. I also serve as one of NASA's champions for open science. Thank you to Annalise, Kuhn, and Anil for the invitation to speak today. I'm sorry I'm not able to join in person, but I'm very thrilled to be able to participate at a distance. Today I'll talk to you about revisiting global water resources from the IHD using modern tools like numerical models and remote sensing from satellites. The focus of the talk will be on the world's rivers. I have an animation of how water flows down the arteries of our planet. Here on the left, the thickness of the blue lines varies with time as a function of how much flow goes through them. This is from a computer model, and it helps illustrate the duality of rivers. They have mighty flow, but a tiny storage. And the mighty flow makes river water the most renewable source of fresh water, but it also makes it one of the most devastating causes of natural disasters around the world. In this chart, number one disaster by type in the number of people that are affected by floods. So we have some knowledge about the world's rivers from the International Hydrological Decade. Happy birthday to IHD and to the Intergovernmental Hydrological Program. The IHD finished in '74. Its goals were to help unify the fragmented field of hydrology, develop a global understanding of water resources, and also provide comprehensive global water data. Its key achievement is a monograph. I have a copy here, which I got on eBay, and this book has everything global water cycle related. Today I'll focus on river water, specifically on the storage of water in the world's rivers and also the discharge that rivers transport to the ocean every year. And our knowledge has evolved a little bit, but actually not that much in the past 50 years on how we understand the world's river systems. The numbers from the IHD are at the top in bold. In the top chart and table for global discharge to the ocean, and at the bottom for global river water storage. The former is in cubic kilometers per year, volume per time, and the latter is in cubic kilometers in volume. Now, it turns out that 50 years ago, we already had access to pretty good numbers, which is quite impressive knowing the tools that our colleagues had access to at the time. The knowledge has evolved a little bit. You'll see some numbers going from up to down with time, focusing on the past 10 years. The overall numbers have remained relatively consistent, at least in order of magnitude. What we have advanced on in the past 10 years or so is we now have a better understanding of not only the long-term mean, but also the variability throughout the annual cycle. And that is really important to help manage for the best days and the worst days of our access to water. So some changes in the mean, but mostly new information on the amplitude of the signal. And that information was partially enabled by information we've gathered from Earth orbiting satellites. I have a slide here with a variety of Earth orbiting missions. It's very NASA and ESA centric, but these data sets are publicly available to all, everybody around our world. All of these missions, whether or not they were specifically designed to observe the world's rivers, lakes, and reservoirs, they do. And there are many aspects, including water quantity, like water surface elevation or water extent, and water quality, like water temperature or water composition, that can be gathered by these satellites, that is available to all, and that allows us to help better assess stores and fluxes in the world's rivers. Now, beyond satellites, we also have incredibly important information on the ground for ground truthing. I'll mention the Global Runoff Data Center, of which you have a map of in situ stations here on the right-hand side that helps us confirm or advance remote sensing observations. We can use that together with a description of where the river systems are on the planet, the hydrography, the blue lines on the map, and numerical models for the atmosphere, the land surface, and for the rivers to help us create the best possible picture of our knowledge of where water is at any point in space and in time, including the past and also right now. So why would we want to do that? Because we need to help bridge science and society for sustainable water management and mitigation of water-related disasters. Everybody needs water. The United Nations declared safe access to fresh water for drinking and sanitation a human right in 2010. So everybody needs water. There is more and more people on our planet. 200 years ago was barely 1 billion, and we're now over 8 billion. Now it also turns out that rivers flow across political borders. If you're upstream, that's great. If you're downstream, you might just get what's left over, and that includes pollution from upstream areas. And so that can create some geopolitical tensions. So where do we go from here? We have a shared future. We need to collaborate for resilience. I mentioned that rivers are one of the key aspects of surface water, water management, water resources management, also water-related disasters. There are still knowledge gaps that persist despite the foundational estimates from the International Hydrological Decade. We need to merge new tools like satellite and models with in-situ observations. Integration is key for informed decision to help with water security, and sharing these data sets in an open manner might help us have educated conversation with everyone on the planet. I'll leave you here with a picture of the launch from the Surface Water and Ocean Topography, and I thank you for